With the insertion of a little math, Sandia National Laboratories researchers have shown that neuromorphic computers, which synthetically replicate the brain's logic, can solve more complex problems than those posed by artificial intelligence and may even earn a place in high-performance computing. The findings, detailed in a recent article in the journal Nature Electronics, show that neuromorphic simulations employing the statistical method called random walks can track X-rays passing through bone and soft tissue, disease passing through a population, information flowing through social network. Newly discovered applications range from radiation transport and molecular simulations to computational finance, biology modeling and particle physics. In optimal cases, neuromorphic computers will solve problems faster and use less energy than conventional computing, he said. What's exciting is that no one really has looked at neuromorphic computing for these types of applications before. Sandia engineer and paper author Brian Frank said, "The natural randomness of the processes you list will make them inefficient when directly mapped onto vector processors like GPUs. Then we showed that our algorithm can be extended to more sophisticated diffusion processes useful in a range of applications. The claims are not meant to challenge the primacy of standard computing methods used to run utilities, desktops and phones. There are, however, areas in which the combination of computing speed and lower energy costs may make neuromorphic computing the ultimately desirable choice," he said. There can still be a high cost for moving data on or off the neurochip processor. As you collect more, it slows down the system, and eventually it won't run at all, said Sandia mathematician and paper author William Severa. Like the brain, neuromorphic computing works by electrifying small pin-like structures, adding tiny charges emitted from surrounding sensors until a certain electrical level is reached. Then the pin, like a biological neuron, flashes a tiny electrical burst, an action known as spiking. But because the process only depletes energies from sensors and neurons if they contribute data, it requires less energy than formal computing, which must poll every processor whether contributing or not. The conceptually bio-based process has another advantage. Its computing and memory components exist in the same structure, while conventional computing uses up energy by distant transfer between these two functions. The slow reaction time of the artificial neurons initially may slow down its solutions, but this factor disappears as the number of neurons is increased, so more information is available in the same time period to be totaled, said Aimone. The process begins by using a Markov chain, a mathematical construct where, like a Monopoly game board, the next outcome depends only on the current state and not the history of all previous states. Beginning with the Markov random basis, the researchers used Monte Carlo simulations, a fundamental computational tool, to run a series of random walks that attempt to cover as many routes as possible. Particles are simulated in a process that mirrors the physical process. The energy of each walk was recorded as a single energy spike by an artificial neuron reading the result of each walk in turn. This neural net is more energy efficient in sum than recording each moment of each walk, as ordinary computing must do. This partially accounts for the speed and efficiency of the neuromorphic process, said Aimone. More chips will help the process move faster using the same amount of energy, he said. The next version of Loihi, said Sandia researcher Craig Vineyard, will increase its current chip scale from 128,000 neurons per chip to up to 1 million. Larger scale systems then combine multiple chips to a board, Perhaps it makes sense that a technology like Loihi may find its way into a future high-performance computing platform, said Aimone. Video. U2.be/o_8e26 Aksekfi J. Darby Smith, Aaron J. Hill, Leah E. Reeder, Brian C. Frank, Richard B. LaHook, Ohas Parekh, William Severa, James B. Aimone. 2022, March 10. Brain-based computing chips not just for AI anymore. Science Daily. Retrieved March 10, 2022 from ift.tt/FHT4 Ju-Do, Sandia National Laboratories. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.